The question is simple, that you have been given two integers n and k. Okay, this n and k are integers for sure. I think that is already given, so no need to write. And this value k, you can assume for now that this is greater than equal to 0. For now you can assume that k is greater than equal to 0. And I want you to output n raised to power k. So I basically want you to output n raised to power k. For example, if n is equal to 4 and k is equals to 6, then I want you to output this value, whatsoever it is, 4 raised to power 6. Okay, how much time will you take to solve it? Your complexity should be in terms of n and k for me to understand. Yeah, so what should be the complexity? Yeah, it will be order of k. So you can write a simple for loop which runs for k times and then gets your job done. But is there a faster way to do it? Modular exponentiation is the name for the technique that we are going to learn. Fast exponentiation, basically, not exactly modular exponentiation. So this is a kind of exponentiation thing that you are doing, order k by 2. I think you can manage to do in order k by 2 also, but can you be more efficient? The answer is yes, you can be more efficient, and we'll all see how we can be more efficient. Yeah, we can do it in log k time. So see, the idea is the same. The idea is divide and conquer only, that we just learned, and now we will learn how we can actually apply that idea to get a job done. Okay, so let us all try to understand it. In the last question, you were always breaking this problem into two sub-problems of equal sizes. Okay, it was not always possible for you to maintain equal size, but in that case, maximum difference between the size was 1. Okay, you were trying your best to ensure that the left problem and the right problem are of as equal size as possible. This is what you were trying to do. Can you try to do the same thing over here? Can you break this problem, which is n raised to power k, into two sub-problems of equal sizes? So it can be very easily done, and we'll all try to just understand that how. So if you take a look at this n raised to power k, can I simply write it as n raised to power k by 2 into n raised to power k by 2? Is this equation correct or not? Right? So that's it. If you agree to it, that means rest is just up to you. So what you can do is, if you have to find n raised to power k, then you can invoke a function that finds you n raised to power k by 2, and another function that again gives you n raised to power k by 2. And once you have response from here and response from here, so let's say the response from here is p, the response from here is q. So what should you return? What should you return? You should return the multiplication of both, which is p into q. Now, I want you to use your eagle eyes, use some brain, and tell me, what will be the relationship between p and q? Yes, they will be exactly same, isn't it, guys? Because those two sub-problems are exactly same. So this was the main thing over here. See, in the last question, if let's say you are getting an answer A1 from here, can you comment on A2? If you know A1, can you comment on A2 that you are going to get from the right side? You can't comment it, right? Why? Because those two are different sub-problems. But here, luckily what is happening is that whatever is the sub-problem for left side, whatever that is the sub-problem for right side also. So once you get a P from here, only foolish people will call this, right? That is how your job would get done. So that is the most important thing that you should understand in this problem. So here if you take a look, this node will never ever create this node. This node will just create this node. And similarly this node will now want to call n raised to power k by 4 and n raised to power k by 4. Both are same, so it will not call this. So just here the recursion tree that you will get will be a skewed recursion tree like this. The other branches will not be there at all. And every time what is happening with k, let's try to understand. K is becoming half of what it was. So eventually, can you tell me, n is not changing, right? Only k is changing. So eventually what will be the value of k? Would k eventually get reduced to 0 or not? It would, right? What will you do at this point of time? Will you continue dividing? If you continue dividing even beyond this point, 0 by 2 will be 0 only. So you will end up getting an infinite chain which would never terminate. Are you getting this thing firstly? Right? So it is essential for you to terminate over here. So can I terminate over here? Yes. Because if the exponent is 0, no matter what is the value of base, the answer should be 1, because anything raised to power 0 is exactly equal to 1. So this was the main concept over here. Now there can be some cases that all of us should understand. So let us understand. Let's say you are asked to find 4 raised to power 6. 4 raised to power 6 very well fits with this, because 4 raised to power 6 is 4 raised to power 6 by 2. This is an integer division. Okay, so 6 by 2 will be 3, and here again 6 by 2 will be 3. So this works well. But what if you were supposed to find 4 raised to power 7? For 4 raised to power 7, would this equation make sense? Yes, no? What will be the value of 7 by 2? 7 by 2 will be 3, right? So you would end up writing 4 raised to power 7 as 4 raised to power 3 into 4 raised to power 3. So this is not the right way to do. So can somebody tell me what should I do? And this problem will only arise for odd powers. It will just happen for odd powers. Okay, so odd powers have to be handled in a slightly different way. Can somebody suggest me what should I do? Yes, it is very easy to do. How? Whenever you have an odd power, how much 4 will be missing? So here I see that just one instance of 4 is missing. This is 4 raised to power 6 and this is 4 raised to power 7. So whenever you have odd power, then this thing can be written as, for k belonging to odd numbers, this equation can be written as n raised to power k by 2 into n raised to power k by 2 into n. So this is the one case that you can have separately for the odd powers, and that is how your job would very easily get done. Okay, so because anything that you if you divide k by 2 and you divide k by 2 and you sum them up, at max you can be away from k by 1 unit. Never you can be away from k by more than 1 unit. Okay, so that is the reason you can write it in this way. And now if you can write it in this way, then the things become very easily. So your proper recursive definition is like this, that if you have n raised to power k, then these are the branches. First, termination condition. If k is 0, then return 1. Okay, if k is odd, then this thing should be considered, and if k is even, then this thing should be considered. So given any recurrences where you find that for some input argument there is some relation, for other there is some other relation, if you try to draw this kind of thing, if you clear this out in your mind, then coding becomes extremely simple for you. Okay, so I'll just try to tell you that maybe how I can get my job done over here. So let's say if you are trying to find 4 raised to power 9. Okay, so for finding 4 raised to power 9, the first thing that you will do is you will invoke 4 raised to power 4, right? Now 4 raised to power 4 will return you some value, right? Because that is what you are doing. When k is equal to k is even odd, then you are invoking this, multiplying this by this itself, and then multiplying this by n and returning it. So let's say if this thing returns you x, can somebody tell me what should be the value returned by it? It should be x into 4. Is that clear to everyone, right? The most important thing is never make the second call, because the moment you make second call, that tree starts growing from here again. Okay, so the only thing that I am trying to do is I am trying to skip that second call so that I get just this much and not that entire bulky tree. Okay, so I'll just call this, I'll receive x from here, and now if this was odd, then I'll return x into 4. But if this was even, if this was something like 6, then you would have returned simply x into x, right? In that case, you would have called for this. So what you return is dependent upon this thing. Okay, so coming back to it, if this was 4 raised to power 9, you had called for this, and what you are returning is something like this. Did it make sense, guys, what I just showed to you? Right? Now again, at the level of 4 raised to power 4, you will call for 4 square, and whatever is returned to you, if let's say the value which is returned to you is y, then what will you return? If you got y from your child, then what is it that you should return? Your power is even, right? So you should simply return y into y, correct? Yeah, cool. So if you understand this thing, then the job becomes very easy for you. Now again, let me go down first because returning happens from bottom. So yeah, this will call 4 raised to power 1 and this will call 4 raised to power 0. 4 raised to power 0, this is the termination condition. So this will simply return 1 no matter who the parent is. Now this thing, what is it supposed to return? So for odd value, you return what you got from children, that square multiplied by n. Okay, so you will return to your parent 1 into 1 into 4, 1 into 1 into 4, and that is correct. Why you are returning that? Because you wrote 4 raised to power 1 as 4 raised to power 0 into 4 raised to power 0 into a single 4. This thing is depicted here, this thing is depicted here, and this thing is depicted here. Now what will this return to its parent? It got the value 4 from here, and this thing is even, so it will return this into this, and what is that? 16. Similar for this, what will it return? This is even power, so this will return 16 into 16. But what will this return? This will return this into this multiplied by one more 4 because this was odd, so it will return 16 into 16 into 16 into 16 into one more 4. This is what it will return. Okay, so who will tell me the time complexity of this? How much time is consumed in this task? They say yes. Log of k. That is perfectly correct. Because what will be the length of this? What was the height of this tree? Every time your size was becoming half, right? Here also this thing is becoming half. So this thing becoming half will get to 0 in log k steps. Log k base 2 steps. Is that clear to everyone? In log k base 2 steps, this will become 0. And at every level, how much work you are doing? You're just doing order 1 work because there is just one single multiplication that you are doing at any level. At some like here you did 1 multiplication, here you did again. So at some levels you will do 2 multiplications, and at some levels you will do 1 multiplication, but on an average I can say that at every level you are just doing order 1 multiplication. So the log k base 2 will be your time complexity. Now let's say if I have to write the code for this, I'll very quickly write that as well. So how's that going to look like? So let's say I have a function int power, this takes in n and takes in k. Okay. Now what should be my first condition? It should be my termination condition. So if my k is equal to 0, I should simply return 1. Okay. Otherwise what am I supposed to do? I'm supposed to call one of my children because left and right both are same. Okay. So what I can do is I can call power of n comma k by 2, and this will return me some value which I will capture in x. Okay. What should I do from here? Should I simply return x into x after this line? Is it right to do? No, that is not right to do. I need to check whether the exponent was odd or even. So I need to check whether the value of exponent here was even or odd. So if I see that k was even, then I am simply supposed to return x into x. Otherwise, I am supposed to return x into x into, that's it, right? Now you can see that again, these log k levels that were there, at every level either 1 unit operation or 2 unit operation. So you can generalize that on average order 1 operations at each level, and that is how you have been able to solve the problem. Okay, cool. Now tell me one more thing. See, this was just a luck by chance here, and this can happen at multiple occasions where you will see that the left and right child are exactly the same. So if you have called this, you do not need to call this. Okay, so be vigilant about that. In that case, you can save a lot of time and you can optimize your complexity to even better than order k. You can become order log k. Okay. Now tell me one more thing. Here I had divided my problem into 2 parts. Instead, can I divide my problems into 3 parts? Can I divide it into 3 parts? I can do that also, right? How I can do? What should be my exponent so that I am able to divide it into 3 parts? It should be k by 3, correct? So I can write n raised to power k as n raised to power k by 3 into n raised to power k by 3 into n raised to power k by 3. Okay, so again, if you take a look over here, so if there is a function like this has got 3 children, n raised to power k by 3, n raised to power k by 3 and n raised to power k by 3. Left child, middle child and right child. If you called your left child, would you want to call this or would you want to call this? No, because all of them are exactly the same. So if let's say left child returns you a value z, what will you return? You should return z cube, isn't it? Yes, no? Okay, but do you think here more conditions will come? Here more conditions will come, right? Because if you have to find n raised to power k where k is a multiple of 3, then this equation will agree, and this will agree very well, okay? Because it is being clearly seen here that n raised to power any multiple of 3, let's say n raised to power 6 can be written as n raised to power 2 into n raised to power 2 into n raised to power 2. But how about something like n raised to power 7? This is not equal to n raised to power 2 into n raised to power 2 into n raised to power 2. Here some powers of n are missing. Can you tell me how many powers of n are missing? For n raised to power 7, exactly 1 power is missing, okay? Similarly, how about n raised to power 8? For n raised to power 8, how many powers do you think will be missing? There will be 2 powers that will be missing. So for n raised to power 8, you would want to write n square into n square into n square into n square. So here the equation that you should be writing should be in this way, that if you are trying to find power of nk, then of course your termination condition should be if your k is 0, then you should return 1. Now, if k mod 3 is 0, then you can simply return n comma k by 3 into n comma k by 3 into n comma k by 3, right? But if your k mod 3 is equal to 1, then what you are supposed to return is this entire thing multiplied by 1 more power of n. And if that mod is equal to 2, then you are supposed to return this entire thing, whatsoever it is, that multiplied by 2 powers of n. So there will be these many conditions. So here you just had 2 conditions, because modulus with 2 can either be 0 or 1, but modulus with 3 can be 0, 1 or 2, so you will end up having 3 conditions. What will happen when you break this problem into k parts? If you break this problem into k parts, that is as good as simply running a for loop, isn't it? Yeah. Great, so I think you can code this and this is how you can get your job done. Same logic can be given here also. For finding maximum in an array, I broke it into 2 parts. You could have broken it into 3 parts also, but there you would have seen more time complexity. Let's do another problem now. This thing is also called as fast exponentiation, and this is very how to handle overflows here if given to do modulo. I think you can handle very easily. Why you can handle? Because there are just multiplications that are happening, right? Since just multiplications are happening, you know what is the value of a into b mod m. That is a mod m into b mod m whole mod m. So while you are multiplying, take mods also. Okay. Is that clear to everyone? Did everyone understand how to handle if the values of n and k are, let's say, extremely large? Okay. Great. Tell me one more thing. If the input given to you is something like 2 raised to power minus 5, how will you solve this? Here I said that my k was positive always, but what if k is negative? Is this always a case that binary division is efficient? Mostly yes. I will not generalize, but mostly yes. How can you solve this problem, 2 raised to power minus 5? I think it is very easy, right? So for finding 2 raised to power minus 5, don't you think if you find 2 raised to power 5, and if let's say this value is y, then the answer of this should simply be 1 by y? Isn't it, guys? Yes, no, what do you think? So don't get afraid. This was a question which was once asked also in Amazon's interview. So you are supposed to do nothing, just use your common sense that to know this thing, don't digress. First find this thing, and you know how to find this thing. If you can find this thing, this should simply be reciprocal of whatever it is. But here, this y, should it be integer or should it be double? What do you feel? Because you have to find its reciprocal and return the decimal answer corresponding to it, so that y should be double. So the values that you should pass to the function should be of double type. Okay. However, the most important part was to take the reciprocal and simply find n raised to power x instead of n raised to power minus x. Okay.